when we look at the energy momentum, that is wave vector relationship, we find that energy equals h cross squared over twice m k squared for free electrons. Now, if we differentiate this expression for group velocity, we can find dVg dt. This quantity is h cross inverse d2 epsilon dk dt equals h cross inverse d2 epsilon dk2 dk dt. This is what we obtain. We know that dk dt, this quantity is force over h cross, and if that is this quantity, then dVg dt, that is this quantity, can be written as 1 over h cross squared d2 epsilon dk2 times the force. So, force is given as h cross squared over d2 epsilon dk2 times dVg dt. If we look at this equation and compare this with the Newton's law of motion, then we find that this quantity is force, this quantity is the acceleration, it is the rate of change of the group velocity, therefore it is the acceleration, and this quantity represents mass. In analogy with Newton's law, that means we can write, if we have m star equals effective mass, which would be actually a tensor, 1 over m star tensor we are writing, mu nu are the components, it can be written as 1 over h cross squared d2 epsilon k dk mu dk nu. This is because along different directions the effective mass in general could be different. Therefore, we need to write down it into a tensor form, although if we have perfect kind of a crystal, perfect kind of a system, the effective mass may be a scalar quantity as well, but in general it is a tensor. So, this is the situation for anisotropic case. For isotropic case, we can write 1 over m star equals 1 over h cross squared d2 epsilon dk2, where the effective mass is a constant. Now, what does effective mass physically mean? We found within nearly free electron approximation that the wave function corresponding to the parabolic part of the band can be expressed as plane wave, that the plane wave function is with a normalization constant e power I k x, and the momentum was h cross k, and the wave component, that is e power I k minus g x with momentum h cross k minus g. This is small and increases only slowly with increasing k. So, in this kind of a region where the electron behaves more like a free electron, we have the effective mass m star is nearly equal to the real mass of the electron. Near the Brillouin zone boundary, this component k minus g component is quite large, and when this grows large, a single electron in an energy band may have positive or negative effective mass. Negative effective mass occur near the top of the band. So, narrow bands have large effective mass and wide bands have small effective mass. This you can find from the expression of the effective mass. Now, let us discuss about the effective mass in semiconductor. In many semiconductors, it has been possible to determine the effective mass using the cyclotron resonance. How do we do that? The effective masses of carriers in a doped semiconductor, say we have p type or n type carriers, and they can move very rapidly in the system, and if we put them under the influence of an electromagnetic field, then there is a cyclotron resonance in the semiconductor. Let us consider that the carriers are accelerated in a helical orbit about the axis of a static magnetic field. So, we are applying a magnetic field with, so the magnetic field is static, and if we make the electrons or holes, that is the carriers, move along an orbit, it will have an angular frequency, cyclotron frequency, and we will reach a resonance. So, if the resonance cyclotron frequency is given as omega c, we can write it as E B over m star c. In c is the velocity of light in CGS unit, and the expression of this cyclotron frequency in SI unit would be E B over m star. So, what are we doing? We are applying a static magnetic field and making the electrons or holes, that is the carriers, move about that magnetic field. M star is the appropriate cyclotron effective mass, and if we reach the resonance by applying a radio frequency electric field perpendicular to the static magnetic field, then we will make the electrons move along the circle. Then from the magnetic field and the resonance frequency, we can find out the effective mass of the system. Now, holes and electrons in this kind of an arrangement rotate oppositely. So, here what kind of situation we are considering? We are considering a magnetic field applied in this direction. An electric field is radio frequency electric fields, that is, it moves along both directions, changes its side. This is applied here. So, the electrons may be made to orbit like this, and when it reaches resonance subject to this electric field, then at resonance we can find out the resonance frequency subject to the electric and magnetic field, of course, and then we can find out the effective mass from this expression. This is how we can determine the effective mass from experiment.